Okay, the logistic equation has to do with differentials. Okay, so the logistic equation is a differential. Right. So it's a differential equation. But what it is really detailing is it's a growth rate differential. Okay. So what we're going to talk about mostly today is biology and population rate growth rates and how the logistic equation can address that. Wildlife biologists kind of use this a little bit. Okay, so the logistic equation
is K another constant?
Yeah. K is a constant, and so is A.
Is that Y over A?
Yeah, it is. Okay. K is the growth constant. And then A actually, in the best sense we can put it, is carrying capacity. So you probably remember that from AP Bio. Talked about carrying capacity, I'm sure. Did you do some mathematics around it? Remember?
That was in apes, that was in bio.
It was in
Environmental science.
Oh, it was. Okay.
That's what I did.
So it was pretty basic math then, I bet you, if you did any.
I don't remember.
Bummer. Okay. Okay, so working within this, we have lots of different information we can glean from it. Okay. What's going to happen, so let's just kind of look at this graphic right here, but so you have carrying capacity, right? What's going to happen if the population starts out with an initial value bigger than carrying capacity? Okay, so this is the initial value, right?
Real decline.
What?
Real decline.
Yeah, so we're going to see a decline in the population, right? So and this logistic equation would define that rate of decline. Correct. We can also have the population of 0, correct? What happens if the initial is less than the carrying capacity but bigger than 0?
It'll try and reduce mean.
Usually, we're looking at an increasing population, right?
Does it always have that?
But that,
Does it always have that shape?
no, because you got predators, we have hunting, we have drought years, you have wet years, and a whole bunch of factors go into that. But mathematically, that's what we're looking at for a standard population growth model, right? And then, if the initial value is less than 0, right?
You don't even have population.
Yeah, there would be, like, in context, there's nothing would happen, right? You got no population unless something moves in, which we're seeing right now with, like, wolves and grizzly bears have been reintroduced pretty heavily, protected with the Endangered Species Act near Yellowstone and in Montana, Idaho, Wyoming. Their populations are getting large enough where they're starting to spread, right? So they're entering areas with no grizzlies now that zoos have them, right? So that's kind of a funny thing mathematically. That's what it looks like, okay? But in context, obviously, we can't really have population less than 0. All right. Any questions? The real key here is that this differential defines what's going to happen to the actual population. So again, we're having a solution to this differential like we've been working on, right? And that solution, and this is really nice. You can use separation of variables here to solve this for y equals, for the general solution. Okay. What's nice about the logistic is it has a solution that has the same format every single time. So you can basically memorize it and you're good to go.
So you don't have to do the separation of variables?
No, you don't. So here's the solution to the logistic. You plug your A in, you plug your K in, and then if you need to, you can calculate your constant value based on an initial value. Right. So you might have something like, let's see. Make sure I work this right. Solve dy dt 0.3y times 4 minus y. With.
Does this show up on the A/B test? It looks pretty gross.
You're earning a point here. It'll probably show up. Usually they'll give you like, so what I've seen, they'll give you a logistic equation and they'll say what's the carrying capacity of the moose population. Right? Or what's the rate of growth? Or what's the general solution? These are like the basic questions we're looking at. Keep in mind again that your book will denote this differently than we do. Right? I don't know why, so I can't call it stupid, but it would seem that way at front. Yeah. Okay, so solve dy dt equals 0.3y times 4 minus y with initial condition y0 equals 1. Okay, is that formatted like the logistic equation? Keeping in mind you have to have a 1 here. Is there a 1 there?
No.
How do I make it a 1?
Just divide by 4.
Yeah. Take a 4 out, right? So 4 by factor of 4 out. I now have 1.2y times 1 minus y over 4. Correct.
When you have 4 dy dt, or 1 dy dt,
Sorry.
when you have to make that 1/4 dy dt,
This?
because if you divide by 4 you divide by 4 on the line.
Here we divide by 4,
Yeah.
and we divide it by 4.
Yes. So it'd be 1/4 dy dt equals.
Well, here?
Yes.
No,
Why?
because we haven't taken a 4 out here. All we've done is move it. Right. We've just factored a 4 out. There's no 4 movement over here. Okay. So given this is our logistic now, here's K, and that's A, what's the general solution? Just follow format, right? Y equals A over 1 minus e to the negative K T over C. You didn't have to use separation of variables or anything, it's just there for you. Okay. You, stop it.
Doesn't make sense.
Well, if you want it to, I can show it to you.
No.
But it requires integration by partial fractions, which you don't know yet. That's January.
Nice.
Okay. How do I solve for the constant?
Well, condition. Solve for C.
So you 1 equal to over 1 minus.
Yeah, that would be the hard way. Like, you know how to do it, right? Plug 0, 1 in and solve.
Yeah.
Okay, that's an option. You can also use this formula if you want to. I think it's A. Yeah. Again, making your life easier. Only we're making it harder by adding something. So the growth, the constant here will be 1 over 1 minus 4, which is 1/3.
Are we gonna make cards for this?
Yeah, for sure. And you end up with y equals 4 over 1 plus 3. How do I know what y0 is? How do I know it was 1?
Is it initial point?
Yeah, it's right there. And then you know how I transfer this to, so dividing by negative 1/3 is the same as multiplying by negative 3, which is plus 3. Okay. So there's a basic logistic equation solution problem. Okay. Again, just memorizing formulas and plugging stuff in where you know it's supposed to go. Okay, here's a word problem, which is how these do pop up most of the time. All right. Deer population grows logistically. Fantastic. With growth constant K. .4, and we put units on here. And to be honest, I have no idea what the -1 means because I've never really tried to understand it. In a forest with carrying capacity (1,000 deer). What's the logistic equation for this? We'll call it P.
24 y.
Well, in our case, P. Whatever.
1 minus y over 1,000.
Okay, there you go. Right is a logistic, very easy to write. Find the deer population if the initial population is 400. Yeah. Should make that a better question. Find the deer population equation. So what are we asking you to do here?
Find the solution.
Yeah, just write the solution equation, right? So again, that's P of T equals,
A over
okay, so 1,000 over
1 minus
1 minus
E to
E.
the negative 0.4 T.
Over a constant, right? And then how do we find that constant?
C equals y0 over y0 minus
Negative
2/3.
2/3. So we can rewrite this.
Wait, what? How do you get 3 halves?
This is divided by negative 2/3, so when you copy that flip.
Yeah, that was multiplied over.
Okay. All right, how long does it take to reach how long does it take the population to double?
You said 2,000 has 100 people? Solve this one?
No,
Why not?
the population's not 1,000.
Say 2,000. That'd be double over that.
Yeah, but 1,000's the carrying capacity.
Oh,
What's the population?
800.
400. So 800 equals 1,000. 1 plus 3 over 2 e to the negative 0.4. Right. And now you have a big algebra problem.
Can you solve that one?
How?
Yeah. Where do you start? Do you multiply the bottom across?
Yeah, that's where I would start. So 800 plus 800. Ooh, I forgot to.
9,800 plus 12.
Yeah. All right, next.
Subtract.
Subtract 800. been using inverses for a couple steps now. How do you get rid of E?
It's natural law.
Yeah, the inverse is natural log, right? So that, goodbye, negative 0.4t equals natural log of 1/6.
What would the time of natural log 1/6 look like?
It's a negative number.
So you have to multiply the negative across, make it positive?
Right.
I thought natural logs were always positive.
No. Natural logs are not. The y values can be negative, the x's cannot. So at 1 is your transition point. So you can have negative natural log values, but no negative x values, right? Yeah, so, anybody know what the natural log of 1/6 is?
Well, then you have to multiply the 0.4 across, or you do that after you evaluate your natural log.
Yeah, so t is negative, you're going to divide it actually, natural log 1/6 over negative 0.4. That's going to give you some number.
It's 4.47.
Please release the cheerleaders that are traveling for state cheer. Go Cardinals!
Is that in years?
T's and ears. If only deer populations grew that fast.
Yeah, that'd be insane.
That would, imagine the deer population in Colorado doubling in
4 years?
4.5 years. The problem with this equation is it assumes perfect conditions. No predators, no hunting, no drought, no hard winters, nothing of that nature, right? So the wildlife biologist is gonna have to take those items into account. And I could show you Unit 44 deer management draft that I got about 2 months ago. They're trying to increase the population of the herd because it is like 1/4 of the carrying capacity of the habitat. But there are a lot of bucks and they're big. And the hunters don't want the big bucks to go away. So there's kind of like this game that they've got to play, right? So, but it involves a lot of this conversation of carrying capacity versus everything, all the other factors. So, I'm gonna have to go to my computer. We switched our schedule up a little bit. But again, your real thing here is memorize those formulas and be able to interpret them. Okay. That's not the one I wanted. Okay, it's 9.4. And a couple of free responses. One of those might involve a logistic. I don't remember enough. Not a whole lot of problems.
No.